Hi, welcome to another video in my series on numerical integration. Now, in my previous tutorials on the trapezium rule and Simpson's rule, I showed you how we could get an approximation to the integral f of x, some function of x, integrated with respect to x, going between the limits x equals a to x equals b. Remember that if we integrate some function of x between these limits, if the graph of y equals f of x is above the x-axis between x equals a and x equals b, then this integral represents that area. Now, this integral, as I pointed out in those tutorials, is sometimes difficult to work out. So we just need to get an approximate value for it. And with both the trapezium rule and Simpson's rule, we took our area and divided it up into strips of equal width. And the trapezium rule, we join the tops of these strips with straight lines. And by working out the area of the trapeziums, adding them together, we got an approximation to that area, which was then an approximation to this integral. The only problem with that method, though, was that the trapezium rule works well when your curve tends to be fairly close to a straight line. However, when it's curved like we have here, then I showed you that Simpson's rule was a better approximation to this integral, because what we did was we approximated the tops of these strips by using parabolas. Now, with the mid-ordinate rule, we have another way of approximating this area. And it gets its name, the mid-ordinate rule, because when we take the ordinates, the x values across here, where I've got these strips, if we take the midpoint of them, let's just say we take this midpoint of this strip and we go up here, like so, onto the curve, and repeat this for each one of these strips, taking the midpoint then of our x values or our ordinates across the x-axis here. Then what we do next is, by drawing rectangles through that midpoint there, back down to our strip, what we do is we start to approximate the area under the curve to that of the area of the rectangles. You can see, for instance, in this rectangle that I've drawn, you've got a little bit of area here that's missed out of the rectangle, but because this rectangle extends outside the curve, well, they're much the same. And if we draw another rectangle in here, say, okay, we're going to get something like that, and down there, like so. And from this point here, if we construct a rectangle like that, and down there, you can see this area here seems to kind of balance out that area there. And we've got a final rectangle in this one. Not so clear with this one, okay, but hopefully you get the idea. Now, I've only just done this with 4 strips here, just because I'm limited with room. But obviously, the more strips you have, the closer this is going to tend to the area under the curve. Now, if we let the first ordinate at a be x0, then this one here will be the ordinate x1. This one would be x2, and so on. It would go on all the way down until we got to the last one, which was xn. So we've got x3 here in this one would be x4, so there would be 4 strips. Now, the width of each strip, let's denote it by h. We tend to use h in both the trapezium rule, Simpson's rule, and now we've got it in the mid-ordinate rule. h, the width of a strip, is going to be given as b minus a, and it's divided by however many strips we've got. Let's just say we call it n. Okay? So if we're going to work out an approximation to the area for just these 4 strips, for instance, what we're going to do then is to work out what that height is here, because it'll be the height of the rectangle, the height or y value for this particular value of x, the mid value between our coordinates here, and multiply that by the width h. Again, we'll repeat it here. We'd add the area of this rectangle, which would be the height here, the y value given by the mid value of x between x1 and x2, and times it by h. And we'd repeat this process for however many strips we've got. And then total those areas together, which would then give us an approximation to our integral. Now I'm only just dealing with 4 strips here, but there's going to be generally, let's say, n strips. Now, if we call this first x value x0, then the one in the middle here between x0 and x1, let's call that, say, x with a subscript to half. And the one between x1 and x2, well, that's going to be x1 and a half. I'll write it as x with subscript 3/2 though. And it's going to go on like this, right to the last value, which is going to be xn. So when it comes to working out an approximation to that integral then of f of x dx integrated between x equals a and x equals b, we know that what we've got to do is to sum the areas of the rectangles. Now if we take the first rectangle here, its height, okay, up here is the same as the height given by the dotted line. And that's going to be when we substitute x half, the value of x, in between this value of x and this value of x. It's going to be that value, f of x half, and it's going to be multiplied by h, the width of the strip. And when we come on to the next rectangle, it's going to be the width of the strip, h, multiplied by its height, which is the same as the height of the dotted line here. In other words, f of x 1.5 or f of x 3/2. And we're going to be adding all these rectangles up until we get to this last rectangle. And on the last rectangle, it's going to be h times its height. Its height is the same as f of xn minus a half. Now if we were to factorize this, what we would get then is, if we were to pull out h, we've got, this is h times the sum of all the heights of the middle ordinates. Okay, and so really we get the name the mid-ordinate rule. So this then is our basic formula. Okay, now I'm going to do a few examples using this. So what we'll do is we'll just put that formula back at the top here. And it's also useful to see this formula in a worded form. What we're doing is for h, it's the width of a strip. And then for all these values here, we're multiplying h, the width of a strip, by the sum of all the heights of the midpoints of the strips. So what I'd like to do now is just to do a couple of examples that demonstrate how easy it is to apply this particular rule. Now, the first example I want to do is to integrate with respect to x, we'll just put it down here, integrate with respect to x the function x squared plus 1. Okay, we'll integrate that with respect to x, and we'll go from x equals 1, say, to x equals 5. Now this is a very easy integral. We could do this, we could easily integrate it, get the exact value. But what I want to demonstrate here is, let's just pretend that this was a very awkward integral, that we had to find an approximation for it. What I want to do though is show you that the approximate value, just show you how close it is to the exact value, which I'll do for you as well. So with this, what I'd want to do is just draw up a sketch first of all of our graph. So we've got our axes, okay, we've got our x-axis here and our y-axis, and we'll let f of x be x squared plus 1. So that's going to be a graph that's going to look, say, something like that. We'll mark that in as f of x equals x squared plus 1. And we're integrating this between the limits then x equals 1 to x equals 5. And to make this quite quick, we'll split this up into two strips. So we'll have a strip down here, okay? So we've got our two strips, so this will have an x value or ordinate of 3. So what we're going to do is now take the midpoints of each of these strips. So this one will be here at the point where x is 2, and this one here will be at the point where x is 4. Let's mark those values in then. We've got 2 and 4. And what we're doing is considering rectangles drawn at these mid-ordinate values. So we've got a rectangle there, okay, and we've got a rectangle across here. Just squeeze that in there. So using our mid-ordinate rule, we've got to work out the width of each of these rectangles. And it's pretty obvious, it's 2 units. But if we didn't know, all we've got to do is say that that width h is equal to the upper limit 5 minus the lower limit 1. That gives us 4 units. That's telling us that width across there. And we're dividing that up into 2 strips. And dividing that gives us 2. So the width of our strip, h, across there, okay, let's just mark it in as h, is clearly 2 units. So according to our formula here, this integral is going to be approximately h, the width of the strip, which we can see is 2. I'll write it in green just to colour code it. Then it's multiplied by the sum of the heights of the midpoints of the strips. So the first midpoint is when x is 2, and we're looking for that height, which is going to be f of 2. And to this we add the height here, which is going to be f of 4. So it's just a question of putting these values in. We've got 2 times then f of 2, so if we square 2, 2 squared is 4, plus 1 is 5. And then f of 4 is going to be 4 squared, which is 16, plus 1 is 17. And so what we've got here turns out to be 44. So that integral is roughly 44. Now, what would the exact value be? Okay, let's just work that out for the exact value. If we're working out the exact value, let's just put that integral going from 1 to 5 of x squared plus 1 with respect to x. Then if we integrate this, the x squared is going to be x cubed over 3. And the integral of 1 with respect to x, well, that's going to be x. And we've got our limits then going between 1 and 5. And notice it's equal now, not approximately. And if we work this out by substituting the 5 into here for x, and then subtracting what we get when we put the 1 through, you'll find that you get 45.3 recurring. So you can see how close it is to our approximate value. Okay, well that's that example. Let's just section that off. Now I've got another example here where what I want to do is look at an integral where we take 4 strips. So using 4 strips this time, okay, what I want to do is estimate the following integral. And this integral is not one that would be generally easy to do. And that is we're integrating 1 divided by 1 plus root x. Okay, with respect to x going from 2 to 10. So to do something like this, we're going to have to approximate it. You might like to even have a go at this one, so I'll give you just a moment to pause the video, come back when ready, and you can check your work solution with mine. Okay, welcome back if you had a go. So if I was doing this, what I'd want to do is just draw up a quick sketch first of all, just so that I can get an idea of what's going on. So I've got my axes, x and y, and assuming that, well, don't even really need to know what this graph looks like, you could just draw any wavy line, but I think you'll find that it's going to look something like this, because as x gets bigger, this is going to get smaller. Now, we're integrating this between x equals 2 and x equals 10. So if I was just to put 2 there, and we'll say we have 10 down here. Now I've got to divide this up into 4 strips. So if I cut it into 2 strips, well then this mid value here is going to be when x equals 6. And if I cut each of these strips again in half, we create our 4 strips. So this value here is going to be at 4, and this one here is going to be at 8. Now we're taking our mid-ordinates, okay, so we're going to have one halfway between 2 and 4, which is going to be x equals 3, halfway between 4 and 6, that's going to be 5, halfway between 6 and 8, that's 7, and halfway between 8 and 10, that's going to be 9. I'll just write them in. We've got 3 there, 5 there, 7 and 9. Okay, so there are mid-ordinate values. And what we're doing then is constructing our rectangles at those mid-ordinate values. Okay, something like this. Okay, hope you can see that. It's a bit squashed in. But there's our width of our strip. Okay, we'll call it h. And you can clearly see that the width of a strip again is going to be 2 units. If we didn't know, all you've got to do is do the last value, 10, minus the first value, 2, and divide it by how many strips we're taking, which is 4 strips. So you've got 8 divided by 4, which gives you the width 2. So when it comes to using the mid-ordinate rule, we've got the width of a strip, which is 2, and we're multiplying that now by our heights. And so the first height is given at f of 3. So we've got 2 times f of 3, and to that we add f of 5 plus f of 7 and f of 9. Okay, so that's the sum then of all of our areas of our rectangles. Now, what have we got then? We've got our 2, and when it comes to f of 3, then we've just got to substitute 3 into here, and that's going to be 1 divided by then 1 plus root 3. And if we keep this going for f of 5, that's going to be 1 divided by 1 plus root 5. And then for the next one, f of 7, 1 divided by 1 plus root 7. And finally, for f of 9, 1 divided by 1 plus the root of 9. Okay, well, quite a long calculation to do, but if you get on your calculator, you'll find that that comes out to be 2.3986 and so on. And I'll leave it to you just to give it to any degree of accuracy. Okay, but that is essentially an approximation then to our integral. And that approximation would get better the smaller you made the width of your rectangle, the smaller you made h. Okay, so I hope that's given you an idea, a general overview then of the mid-ordinate rule, and that you can apply this particular formula now to any integral. Okay.